When you come take the test, yeah. Yay! So last we left was about here-ish, I think. We'd been talking about telescopes, and remember I brought in my telescope. It has a mirror, the reflecting telescope. The thing about all of our telescopes is they are gathering visible light. But remember, if you look at all the cousins, all the different types of energies, electromagnetic radiation energies, visible light is just a little sector, just a little sliver. So in studying the heavens and studying the cosmos, we actually need to make use of every little bit of energy that's coming from stars and the hiss of the Big Bang and galaxies and that sort of thing. So we look at all the different wavelengths. So listed up here are some other wavelengths you recognize. The radio waves, radio astronomy, right? Microwaves, microwave astronomy, you get the idea. Now to gather radio waves or microwaves or gamma rays, okay, to gather them, you can't use the regular typical mirror. You've got to do something different, okay, or the lens, okay. So, so for instance, remember that actually radio waves, and this is one thing I want to remember for your test next week, radio waves are very long. Sometimes they're like, I don't know, like 2 miles long, okay, they're very long. And so in order to make sense of those waves that come from outer space, our telescope has to do one of two things. It can either be very large, or you can have several radio telescopes working together to feed into the same signal. That's called interferometry. And then also I'm going to show you here in a minute the picture of a telescope that you would use to capture those intense gamma rays. Okay, so the thing about gamma rays is they are, on the scale of cousins, they are the most energetic, the shortest wavelength, okay, the greatest frequency. So you need to, actually they would go right through glass. So you really can't use a typical mirror. So this actually is radio astronomy in work. This is a humongous dish, okay? Your book says it is 305 meters in diameter. Okay, so actually 305 meters translates to 1,000 feet, which is longer than 3 football fields. So that is one crazy big dish telescope, okay? But it works the same as the telescopes we talked about last week in that it has, I don't know if you can kind of see this, basically you figure the signals are coming in, okay, this is signals coming in. Okay, this dish is curved, and they are all reflected back to a common focal point. Remember that kind of focal point in our other mirrors, or excuse me, in our other telescopes? Right there is the focal point for this telescope. Is that not cool or what? Alternatively, you can have a set of telescopes that all work together to feed into the same picture, to kind of get a piece of that humongous wavelength, radio wave. Okay, so this is pretty over here. You see some star trails, okay? Not very pretty. But down here is the army of telescopes, radio telescopes. It's called interferometry when all of those radio telescopes work together. I've not been out west and seen these, but I've got a friend that actually has been driving out west in New Mexico region, and you can actually see these roaming the desert. I mean, they aren't roaming. But like the slide says, they're actually on railroad tracks to relocate them. That's pretty cool. So that's long waves, right? Short waves, actually, you need to change it up and use this, it's called a glancing technique. Okay, so gamma rays, well, this is X-rays. So these are X-rays actually kind of hit a glancing blow on this collector, okay, and bring it back to a focal point. So we're going to talk about telescopes in outer space. This is not a photograph, but this is just an artist's drawing of this telescope in orbiting the Earth. So we definitely have our fair share of telescopes orbiting the Earth. That's one of the topics we're talking about in just a minute. Hubble Space Telescope, telescope orbiting the Earth. Okay, and the reason actually that Chandra needs to orbit the Earth is because the rays it's collecting, X-rays, most of those X-rays are blocked out because of Earth's atmosphere. So you're like, dude, you can't be on the Earth's surface because they're all blocked out. Okay. So placing telescopes in outer space. That actually is the Hubble Space Telescope. Can you see the little flappy thing up there? Okay, so one of the things about being in outer space like that is you're susceptible to cosmic energies that you don't want to be susceptible to. So for instance, you've heard of solar storms, and we'll be talking about that. When the sun actually is kind of sending charged particles, it's burping basically, the sun is having a storm, Hubble will want to close this little door. Okay, so there's the Hubble Space Telescope. But I mentioned the Earth's atmosphere, and that's only one reason that you're going to want to go ahead and put your telescope in outer space, okay, to go ahead and look at the heavens so you don't have, the Earth's atmosphere. The other thing is light pollution. There is I don't know how big the movement is, but what is it called? Dark Skies Association. It's like an international group that they are passionate about being concerned about all the light pollution that we've got going on. Okay, so light pollution not only makes it hard for observing the stars, but light pollution also plays havoc with natural nocturnal rhythms of the animal critters and that sort of thing. So light pollution, Hubble doesn't have to worry about light pollution. The Earth's atmosphere, not only does the Earth's atmosphere block out things like X-rays, but just the normal Earth's atmosphere having nothing to, just the normal Earth's atmosphere causes a certain amount of turbulence. If you've ever looked at a star and it's twinkling, okay, that's actually because the Earth's atmosphere is causing it to twinkle. It's like the Earth's atmosphere, it could be perfectly clear when you see that twinkling. But if there's like any sort of heat variations in temperature in the Earth's atmosphere, pockets of air, then it's going to cause that twinkling. And we talked about angular resolution. Remember, angular resolution is your ability to see fine details through your telescope. So actually, if you get this twinkling, this distortion going on, there goes your ability to see the nice, crisp details that you want to see, like the clouds of Jupiter. Okay, so here we have kind of side by side. The smeared out one is, they're actually seeing the same sets of stars. The smeared out one is a land-based telescope, and the other one is a Hubble Space Telescope. So as far as being able to see detail, of course, you can see more on that right one, right? So that is actually a telescope that's orbiting the Earth. So oftentimes, telescopes are built as far up in the atmosphere as you can get, so i.e. on mountaintops. Hopefully dry mountaintops. In meteorology, we talk about this a little bit, but like the island of Hawaii, it's like kind of dry. You're like, really? You're an island. How could you be dry? But I don't know. So this is a figure from your textbook. Can you see the cousins up here? So here we got the gamma rays, X-rays, UV, visible, infrared. There would be microwaves here and radio waves. Okay. So what this is supposed to tell you is that the longer the arrow, the black arrow, means more of that energy can get through to the Earth's surface. So for instance, we see a lot or most visible light can get through the Earth's surface. We're doing pretty good with regard to radio waves. I mentioned the Chandra X-ray. Okay, it needs to be in outer space because really it doesn't, the X-rays don't penetrate the Earth. So if we want to study a celestial object sending us that information, we have to go beyond Earth's atmosphere to do that. So up here, as you probably figure, are a number of telescopes that are orbiting the Earth. Now, it is a busy place up there. I don't know if you've ever kind of dabbled in looking online to see even not the telescopes, but the satellites that are orbiting the Earth. There's a lot of satellites up there. Well, there's a lot of telescopes up there, too. Okay, so these are all telescopes that are orbiting the Earth, studying different energies. Okay, and I just think it is so cool that scientists put together all of that information at those different wavelengths to understand something different about the cosmos, whether it's stars or galaxies or the universe. So the last topic is this. So let's just say you're stuck on the Earth, and but you want to optimize your seeing. You want to optimize. By the way, seeing is the word they use for, is there much turbulence or is it nice and steady? Okay, if the seeing is good, that means that you've got good angular resolution. The air is calm. Okay. But if you're limited to the Earth's surface, actually you can do something with your telescope. I can't, but you can if you have a lot of money. Okay, it's called adaptive optics. Basically, it's so cool. What they do is they send up a signal through the atmosphere, okay, and they identify kind of that would cause the twinkling, and then they take the mirror and they correct for that, like minute by minute or second by second. Okay, so turbulence, correct, turbulence, correct, turbulence, correct. They actually change the shape of the mirror. And so this actually needs to work best with some sort of segmented mirror. Okay, so that's kind of how they get the different shapes to correct for the turbulence. So again, from left to right, you see the same image. Of course, the right one looks like you can actually see two dots. Okay, these stars doesn't look like it's in the visible part of the electromagnetic spectrum. It looks like it's more maybe in infrared. So we see good angular resolution here, poor angular resolution there. So, dun, dun, dun. Okay, so we are going to watch part of a movie now.